Good evening, ladies and gentlemen. My name is Gary Diamond. I'm the president of the St. John Center, the Royal Astronomical Society. Hope you all had a good, safe summer and everybody's gotten their vaccines and keeping themselves safe. Tonight we got a great speaker, and I'm going to get Phil to introduce him.
Okay, thanks, Gary. Tonight we have as a speaker Dr. Chris Hurd from the University of Alberta. Chris has been in planetary science for probably just over 20 years now, and of more recently he has become involved as a are you a PI, Chris? I forget exactly if you are a PI in the or a co-investigator in one of the parts of the Perseverance mission.
I'll come to that. I'm actually what's called a participating scientist. So.
That's it. Yeah. Okay. Sorry, I couldn't remember the right terminology. But Chris is currently involved in the Perseverance rover on Mars, involving its sample selection, where they're looking to collect samples for potential sample return in the future. He comes to that route by being able, in the past, he's worked on Martian meteorites quite extensively and on astromaterials more generally and astromaterials curation. He has a lovely lab in Alberta. If you ever get a chance to visit, it's really cool. And he also obviously teaches and has students and graduate students working in planetary sciences. So Chris Hurd comes to this with a lot of experience, and he's doing really neat stuff on Mars. So I think we should hear what he has to say.
Thanks Phil. Appreciate it. Yeah. Okay, so yeah, this is a real pleasure. Thanks for the invitation, Gary and Phil. And I'm going to talk about this rover mission that I'm really fortunate to be able to work on, giving you a up-to-date status of the rover and how we're exploring Mars and sampling it. We've actually started the sampling process. So I think when I was first invited, I was invited to speak to you in June, and I said I couldn't manage that because things were too busy on the rover, and said, well, if we go until September, maybe we'll be in a position where we'll have sampled, and now we have. So this is exciting to talk about this because basically this rover is now fully operational. It's done at least one time everything it's supposed to do. All right, so starting with the background though. I don't know how many of you realize this if you've looked through your telescopes at Mars, why it's red. But it's red because the surface has rusted over the past 2 to 3 billion years. It's basically a dry desert where the only chemistry that's happened at the surface is rusting. Prior to that though, around 3.5 to 4 billion years ago, it probably looked a bit more like what you see on the right-hand side here, this artist's impression, where it may not have had an ocean per se, but it probably was warmer and liquid water was stable at or near the surface. And so one of the most fundamental questions in planetary science, in this sort of broad planetary science of understanding how planets form and evolve as a system, is why did Mars go from something that was warmer and wetter and to something that, and more potentially hospitable to life, to something that is cold and dry today. And of course, along with that is, if there used to be liquid water, did Mars ever have life? And we need a really capable rover in order to answer that question. And not only a capable rover, but a capable kind of system to answer that, system of missions and sample return to answer that question. If we look at the terrestrial, that is the Earth biological timeline, looks something like this in a nutshell. And so the first familiar fossils showed up around here in what's called the Cambrian explosion. And actually this reminds me of my visit to Mistaken Point in the summer of 2018, which was fantastic. I have to say that was a highlight of the trip for me, where some of those soft-bodied organisms are preserved. Maybe Larry has exposed more, I don't know, that's an aside. But but in terms of the types of, the time frame of Mars change is right around this point in Earth's history. And by that point, we had the first single-celled organisms that could photosynthesize, could actually get energy from sunlight. And they built up structures, which are called stromatolites, which look like this on the right here. And so what should we look for if we're going to go to Mars or send a mission to Mars? We're not going to be looking for our classic fossils. We're going to be looking for microbial and or chemical what are called biosignatures, signatures of life having been there, that are perhaps up to or maybe even more than 3.6 billion years old. So the main goals of the Mars mission are fourfold. The first is good old geology, to understand the context, the setting, understand where the liquid water was, what the environment was. The second is called astrobiology, which is the study of life outside of the Earth, or the limits of life. The third objective is to actually collect and cache samples, which is a really important part of all of those three things work together in ways that I'll hope to show you. And then the fourth one is actually to prepare for humans to go to Mars. So there's a couple of technology demonstrations that kind of pertain to that. So here's our rover. Well, it's a CAD model of the rover. And what you can see here, it looks familiar if you've followed the Curiosity rover, which has been going on Mars for 10 years. This is about the size of a small SUV, and a six-wheeled rover with this mast here that's at the top of it. It's called Mastcam Z, which has a pair of zoomable panoramic cameras. Supercam, which is a laser that can vaporize rocks up to 7 meters away and get their composition. The Meta, which is the weather station that's on the mast primarily. We also have a subsurface radar that can see up to, I think, about 10 meters depth with a resolution of a few tens of centimeters. And then on this arm, which is quite a large, sort of beefy arm, it has the Sherlock ultraviolet spectrometer and its sidekick camera Watson, and Pixel, which is an X-ray spectrometer for interrogating the rocks. And the cylinder sort of thing here is where the action happens for collecting samples. The technology demonstration that's on here is called MOXIE, and this produces oxygen. This is a test bed for trying to produce oxygen from the carbon dioxide in the Martian atmosphere. And I won't have time to kind of go into that, but I'll just say that on April 20th, the first test was successfully done with MOXIE, and they produced just over 5 grams of oxygen from the Martian atmosphere with this. And this is the type of thing that you might think about scaling up several, maybe an order of magnitude or more, and sending to Mars ahead of time to churn away and build up a supply of oxygen that future astronauts could use, both for, obviously for breathing, for habitat, but also for fuel, so that you don't have to bring all the rocket fuel to get home with you from Earth. So that was this sort of the fourth objective there. That's part of that. And that work is ongoing to continue to test that. We also have delivered a Ingenuity, which is a small helicopter to the surface. And this is a series of images that shows how it was tucked up under the belly of the rover and then lowered down onto these 4 feet. And then we drove away about a few meters and imaged it to make sure it was all okay. And this is this technology demonstration is to demonstrate the first powered flight on another planet. It weighs about, it's solar powered. This inset image shows you the solar panels here, which are already sort of dust covered, even just a few hours and days after we set it down on the surface. It's operated by the solar charged batteries, and there's 2 rotors that counter rotate, mounted one above the other. And they have to spin at much faster speeds than a normal helicopter on the Earth, or drone type aerial vehicle on the Earth. They have to go kind of 2,400 to 2,900 RPM in order to get the lift in the thin Martian atmosphere, where the atmosphere is only 1/100th the atmosphere of the Earth's. On the flip side, it does have the advantage that it's on Mars, where the gravity is 1/3 less. So it weighs a third less than it does on the Earth. On the Earth, it weighs about 2 kilograms. So this is a really interesting technology demonstration. It's actually worked quite well, and I'll come back to its success here in a couple of minutes. The rover is also very well endowed with cameras. Some of them I already mentioned, like Sherlock, Watson, and Pixel, and the ones on the mast, but we also have these hazard cameras, or HazCams, on the front and the back that are able to give us the ability to do auto navigation. That is to look for hazards automatically in the landscape in 3 dimensions as it's driving, and the onboard computer will navigate around hazards, around rocks, for example, that are too high for its clearance or things like that. And in fact, just the other day, we set a new record for the distance traveled on Mars with AutoNav, as we call it, of 167 meters. I think the previous record was 100 meters by Curiosity. The other great thing about this rover is that it has cameras that were designed to look at entry, descent, and landing. That is the whole process of getting to the surface of Mars. But to sort of step back and look at the timeline of the mission, the landing site was actually decided. The landing site of what's called Jezero Crater was decided in November 2018 at a community workshop that I was fortunate enough to be able to attend, where we essentially narrowed it down from about 8 or 10 sites that had been previously narrowed down from a previous workshop, and then we're able to put it into kind of the top 3 landing sites. The rover had been designed already and was in the process of being built, and then it was launched July 30th at 9:20 a.m. Your time in Newfoundland, and then cruised to Mars over 6 months and 20 days, and then landed on February 18th of this year, and it's been going strong ever since. This is a beautiful photograph taken from a Cessna about 5,000 feet over Cocoa Beach. Most of the science team had to watch from home, like everybody else, like almost everybody else, on NASA television, which was still exciting, but I can imagine this would be especially exciting to watch a launch from a Cessna flying around southern Florida. The total trip to get to Mars was 471 million kilometers, and that's because of the interplanetary geometry. We had to, of course, catch up to Mars over that over 6-month period. Entry, descent, and landing is worth mentioning here. I don't have time to get into to show a video, but there is a video now thanks to all those cameras that I mentioned. And in fact, I will put it in I think I have a link here. Yeah, I'll put the link in the chat so that you can grab that and watch it later. But that link is essentially a record of in the voice in mission control, and cut in with video from this whole entry, descent, and landing process. It's really quite amazing and worth watching. But the whole thing happened autonomously by the rover, by the spacecraft. Everything that I'm about to describe to you, that's why it's called the 7 minutes of terror, because nobody's controlling this real time, because the one-way travel time for communications at this point was about 11 minutes. So everything was happening 11 minutes ago as the signal was coming in. But the amazing thing about it is that it went from this cruise stage separation to atmospheric entry going, what is it, 5 or 6 kilometers per second or something like that. And then it started to decelerate in the Martian atmosphere. And then the parachute deployed to slow it down. And this was a special parachute, hypersonic parachute, to deploy in the thin Martian atmosphere. And then the heat shield separated. And at that point, the radar locked onto the surface to get a precise measurement of the altitude. Then it started to image the surface, and on board in the computer, it had preloaded maps of the surface of the landing site. And those maps were keyed to whether an area was safe to land on or not. So what the rover then did was to essentially say, okay, it's automatically looking for features on the surface of Mars in this landing area and correlating them to and trying to solve getting lock on relative to the maps in its memory, and it was able to do that. And then the back shell separated, so to take the parachute away, and then this basically sort of like a jetpack started to fire, and that went into power descent. And at that point, the rover computer could guide the rover away from the hazardous areas and set it down in a place based on its mapping, its own mapping, on a place that was safe for it to land. And it did that successfully. And then it went through what's called the sky crane maneuver, which is basically where the descent stage is called, the jetpack, lowered the rover down onto the surface with these tethers. It gently set it down, and then the tethers detached, and the jetpack, having done its job, flew away and crashed. And all of this is documented. So the frontispiece, I guess you'd say, of my talk was actually an image taken from the sky crane from the jetpack looking down onto the deck of the rover as the rover is actually being set down onto the surface of Mars. So watch that video when you have a chance, because it's really quite something to sort of see all of that documented. And I can tell you that my colleague Justin Mackey, who is responsible for all of these entry, descent, and landing cameras, and they're basically GoPro cameras that were kind of certified for space to put on these different parts of the spacecraft, did a phenomenal job. His team did a phenomenal job, and it was incredibly exciting. It was one of the first team meetings, science team meetings online, of course, after the rover landed. I think it was the second or third day we got thumbnail images down from the videos. So they weren't even the full images yet, but Justin could tell that the parachute had opened. He could tell that we had particular video and images that were coming later of all of these different things, and was super excited and got the whole team excited. And then, of course, we had to all keep our lips zipped for that weekend until the NASA folks could put together the video that I sent you the link for. So it was really, really quite exciting to be involved in that. Anyway, so safely on the ground. Of course, we didn't have all of that imagery or anything right away, but within the rover was programmed to take an image through the hazard cameras, from the hazard cameras through the lens cap. So the reason this looks black and white is because actually it was taken only in one band, and there's a semi-transparent, I guess it's a transparent lens cap over top of the hazard cameras to protect it from the dust and getting kicked up from the landing. And so, but it still shows that the rover is sitting in the right orientation, upright, looking out at the horizon with rocks and regolith close by. So it's a successful landing. That first one was taken about 40 seconds after landing and sent back right away. And the second one that I'm showing here was about 10 to 20 seconds after that. And what you can see highlighted in the distance, this plume is actually from the descent stage crashing. So it actually captured the crash of the descent stage after it had done its job of setting the rover gently down on the surface. And then within a couple of days, we ended up with our first images. We stood the mast up. There's a lot of things that have to be checked out to make sure things are working, of course. We stood the mast up, and then the mast cam Z was able to take its first 360-degree panorama. So you can see the deck of the rover. You can actually see a bit of debris on the deck. And you can see actually here in the near distance, you can see these two spots here are from the rocket blast, the jetpack blast, blasting loose material away and exposing some rocks underneath. But you can, and obliterating this dune right here. And you can see these flat rocks, and you can see off into the distance as well. And in the far distance, the mountains there are the rim of the crater that we're in. So the crater that we're in is called Jezero crater, and it sits on the northwest corner of Isidis Impact Basin, one of the largest basins on Mars, at the boundary between what's called the Southern Highlands and the Northern Lowlands, between Syrtis Major and Utopia Planitia. And it's a key location for a number of reasons. One is because it's sitting in this general area. The boundary here is essentially a boundary between older rocks and younger rocks. And if we look closely at the crater itself, it's about 45 kilometers in diameter, and it has these channels or valleys that there's evidence that water flowed in through one and out through the other. And as the water flowed in, it filled up the crater, and so this was a crater lake estimated between 3 and 4 billion years ago. And at that time, this river was carrying sediment along with it, and that sediment, as the water slowed down and dumped into the lake, it dumped the sediment into what's called a delta, and that's what we see here, beautifully preserved. So the thinking here is that this was once filled with water, with river flowing in, another river flowing out, and that this would, of course, contain habitable environments. That is, if you had life as we know it on Earth living there, there was places for it to live. So this is an artist's impression of what it might have looked like. I won't quibble too much, but I don't think the surface of Mars was red at that point for the reasons that I kind of mentioned at the very beginning. But you can get the impression that this was filled with water, and so there are environments perhaps at the bottom of the lake, within the lake itself, or in terms of the rocks where it would be preserved, they might be at the bottom of the lake or at the margins of this ancient lake. And so we've landed inside of this crater. And this is the location. This is our landing site, known as the Octavia E. Butler landing site. It was named that after a science fiction writer who was originally from the Pasadena, California area where Jet Propulsion Labs is based. So we ended up here. The most likely place, actually, we knew we could put the rover down somewhere in this ellipse here that's shown in this diagram, in this image. The most likely place was just off of the delta. That's these rocks up here. But we ended up on the far side of this rubbly sort of area, which is known as Sept for reasons I'll explain. Probably because of that divert maneuver that I mentioned, because this is not a safe place to land. Nor is it a safe place to drive, as it turns out. And so we, after landing and checking out and then starting to do operations, we had to decide on what we were going to do for the first, what's called science campaign, where we're going to spend the first essentially few months to a year exploring. And we knew that we could not go through this area, but we had to go around it. So what we've done, and this is a map up to date as of today, where here's the landing site, and these dots here in white are all the basically the times when the rover has stopped to take measurements, and the lines are driving days basically here. And we're in what's called the green zone campaign. The green zone is defined as a zone that borders along this rubbly area called Sept, around it like this. It's known as the green zone because it's been checked out by what are called the rover planners, the engineers in charge of it, of determining where it's safe for the rover to go. And so the plan is to explore this, take samples, and then to reverse our course and go back around this and around the Sept area. So what I'm going to do now is I'm going to show you a few images from our exploration so far. But one of the reasons why this is, first of all, why is it called Sept? We landed in a quadrangle that had previously been mapped that was named after Canyon de Chelly, the monument in Arizona that's in the heart of the Navajo Nation. And so Sept and other features and targets of interest and et cetera that we have explored in this area are named after Navajo names, or along Navajo names, working in collaboration with the Navajo Nation. And in fact, one of the engineers on the project is from there and helped coordinate that. So which is a really a cool sort of a thing to be able to do. We've since moved into Verdun, to a quadrangle called Verdun. And so everything in that quadrangle, including where we've cored, are French names. So I will switch to that in a little bit. Not to French, just French names. So this is where we landed, and after we landed, this is one of the first images that was released with a bit of very, very preliminary interpretation, not even really interpretation, just a description of what we're seeing. So just dark rocks sort of sitting up in the middle distance, the regolith, which is just another word for soil or loose material, these light rocks known as that we've called pavers ever since. They're kind of flat, embedded in the ground, and these holy rocks that were right under the wheels of the rover. You can see them here, and there's been a lot of debate on the team about what these holes are, whether they're from what are called vesicles in basalts, from gases escaping as magma erupted, or whether they're from parts where the wind spots within the rock where the wind has eroded out less resistant parts of the rock, and the rock was sedimentary. We're kind of leaning towards the igneous explanation now, but there's still a lot more that we have to determine. And remember, at this point, we didn't have all of our instruments available to us. Since then, of course, we've done a lot of work and a lot of other panoramas. This is from what's called the Van Zyl overlook. This is from a little bit further away. We moved away after dropping the helicopter, and this is where we had to stay put for a few days in order to support the helicopter's flights. We had to stay at a particular orientation so we could make sure to have communication with the helicopter. And the helicopter did a sort of up and down flight, then it did an up and over and down flight. And then in the third flight, it did a lot more and went even higher. And this is from what's called the return to Earth camera. It's basically kind of like a modified, again, space certified cell phone camera mounted at a 45-degree angle off the belly of the helicopter. You can actually see two of the feet here on either side of this image. And it's, I forget this is at 5 meters altitude at about 85 meters away from the rover. And it turned out it was able to capture the landing site with a blast zones and the rover itself. Here we are sitting over here. It was a really cool thing. It's done it at least one other time it's been able to take images looking back at the rover. Not only that though, this little spacecraft, this little technology demonstration has gone from technology demonstration to reconnaissance. So originally it was supposed to do 5 powered flights to test this out, and that would be success. It's just recently completed its 13th flight and is about to do 14. And on flight number 12, and you can see this in this map here, the flight paths from Ingenuity are shown here. Some of the first ones testing around the landing site are here, and then it basically followed us, or in some cases led us into this area. This area that we just entered right here in what's called South Sept. Remember I said we can't drive across it, but we decided to take a tow dip into it because the rocks in there are different from the rocks that we landed on. And of course, we want to be able to explore that and get a sample. But in order to do it safely, we had to go carefully. And so what we did with this Ingenuity, this phenomenal reconnaissance helicopter, is to be able to task it to look at the rocks in this area. So flight number 12 was this one here, kind of out and back. And then actually flight 13 has been added to this now, and it explored another area in great detail. And so what it's doing is it's doing recon for us. So this is actually that flight 12. This is the series of images that it took going out and back again. And we're using this to help to plot our path through that area. And we used it to help narrow in on the outcrops that we want to focus in on. It's not the only way that we're doing it though, of course. The rover itself has the Mastcam Z, this up to 110 millimeter zoom that it could do. And so here's an example of that, looking off across Sept from earlier in the mission to a feature known as Kodiak. And this one is quite remarkable to geologists because you can see these inclined beds right here preserved in the rock face, and these flat-lying beds here as well. And in other places, we were able to see boulders up to a meter and a half in size. And in the environment that we're talking about, in a crater lake, a place that was filled with water, this is significant because it tells us something about the environment, how much water was flowing and how much energy it had. It's something about the environment that basically how the water was flowing some 3.5 billion years ago, even before getting up to these rocks up close. So in fact, there's a paper that's about to come out in Science on these observations right here. But what it really tells us is it confirms for us that it was a river delta, And river deltas are habitable environments. And just to come back to that point, this is an environment where if life existed, then evidence of it having been there may be preserved. Here's the thing though, we have this great set of tools, but in order to really say for certain that life was there, we need to have samples back in labs on Earth. And so the part of the rover mission that is nearest and dearest to me is the sample caching system, which is a combination of the coring device, the coring mechanism on the arm, and an incredibly complex set of robotics on the interior of the rover. You can kind of see it here in this series of images. Here's the arm. Right here, the two posts, that the contact sensors for when it goes to either a braid or core. And just in the middle there is, in this case, is a coring chuck to be able to, sorry, not a coring, a braiding bit in order to be able to braid off and get a fresh surface. But the whole idea is that it would do that. It would contact the surface and abrade to get a fresh surface to look at, and then switch out the bit and get it and take a core. So this is an image from the first coring attempt location. So it's up in here where we ended up attempting the core. And this is right down, actually I forgot to point that out, I'll just back up. It's right down here. Basically, what we're calling informally the thumb of Sept as we're coming around here. So this is where the first coring attempt was. And then the second coring that's taken place is at a place called Citadel. I'll show you that in the images afterwards. So this is the target Rubion. And what we were doing in this case, we were targeting these flatline, these pavers, because these are features that you can see, these sort of polygons, these fractures in them and these made up of these pavers. You can see them all over the place in the landing site and all around and from orbit. And in geology, of course, if you're going into a new area, you do the reconnaissance ahead of time using satellite imagery, or in the old days used air photos, and you do the reconnaissance and you say, okay, well, this looks like one particular unit. And that's what the team has done. This is known as the crater floor fractured rough unit. It's been mapped as such. And you see it has these features from orbit. And so when you want to sample, you say, well, we want something that's representative of that unit. So we were going after this, there's one of these pavers. And on the left, just in the sort of the boundary of the shadow that's being cast here, you can see a little abrasion patch. So that's the first thing we did. That was to clear off the rusty dust and any sort of alteration, weathering on the top surface to get a fresh surface. And this target here is called Guillaume. And we're able to put the Pixel and Sherlock spectrometers on that to tell us something about it. And then we attempted the coring. And so we did the coring and it worked beautifully. Again, remember, this is all autonomous. So we send the commands up and then it does its thing and then it sends the results back. So it went through this entire process, incredibly complex when you think about it. The arm has to go out. It has to core, it takes a core, goes into a sample tube. The sample tube goes into the belly of the rover, gets imaged in what's called a cache cam, little imaging device to see the core inside of the tube, and then the tube gets sealed up and that tube gets stored on board. All of that was done and it worked beautifully, except the cache cam images came back and showed there was nothing in the tube. And so this was obviously a little worrisome for the very first sampling attempt in a multi-billion-dollar mission that's supposed to collect some 30 or 40 plus samples. So we looked at it, engineers looked at it, and it turns out that what probably happened is that this rock, we picked the wrong rock basically. This rock is quite weak, as it turns out. It's probably an igneous rock, we think, that has those igneous minerals in it, but they're no longer kind of interlocking crystals like you expect in an igneous rock, in a fresh igneous rock, because they've been altered along the boundaries. And so when it went to core, it's a percussive drilling process. So it's sort of like a hammer drill. And so what happened as it was doing that is it broke up into small pieces, and the pieces just ended up coming out of the hole along with the tailings and just became part of the tailings. So this little volcano here looking thing of tailings is probably where the sample that would have gone into the tube ended up. So we didn't want to make that mistake again. So we would, although it is an interesting place, and we may come back to this area, look for something else to sample on our way back through. But our second target was on this rock called Rochette. And in this case, we're looking for something that was sticking up above the surface that's resistant. And you can see if you have any sort of a geological training, or if you have a geological sort of eye, you can see that it does indeed, it does indeed stick up above the surface, and it's also got these kind of flutes in it, and they're from erosion, and so it's been eroded, but it's still sitting there at the surface. And so we picked this one, and we imaged it, we did an abrasion on it, and then we took a sample. And in this case, instead of having the rover do the whole autonomous thing all the way through and then report back, we stopped after taking the core, and the arm turned upwards about 45 to do, it has a particular stage that it goes through called percuss to ingest, which is basically to sort of make sure that the sample is inside the tube. So we paused at that point and had the mass cam look at it. And that showed this, and it shows you that they did in fact get a core. You can see it there inside. This is the coring bit. So you can see it just inside the coring bit there. And so that was a success. We knew that was a success. One complicating factor was that after it did the percuss to ingest, the core didn't show up anymore. And in fact, we weren't sure whether it had popped out in that process. That was unlikely, but we weren't absolutely sure. So we had to take other images in different lighting conditions to make sure. And sure enough, all that had happened is when it had gone through this additional process of making sure that the sample's in the tube, the sample had dropped down about 4 centimeters, and so into the depths of the tube, and it was hard to see. But we know that we got a 6 centimeter core out of this particular rock, and the cache cam later showed that it was there in the tube safely. And this particular sample is called Mont Denier. And then it was sealed up, and this is an image of the top of the tube after it was sealed, after the cap's been put on. And this is actually an image of the tube itself that was used, tube number 266, in the lab at NASA JPL before it was loaded onto the rover before launch. So it is inside this particular tube in the belly of the rover. Now, following on that success, we wanted to get another sample of the same rock, basically a pair, for reasons that will become clear a little bit later when I talk about the whole strategy for what we're going to do with these samples. And so we then targeted another spot just to the left of Mont Denier, and we ended up getting that one. This is Montagnac in the tube here. And so that allowed us to get 2 samples sealed up in tubes and then be able to drive away. Now, for someone like me, that's really exciting because that's the whole reason I'm on the mission in the first place. In 2018, I applied to NASA to become a participating scientist on the mission, and I was selected as one of 10 people in that call to get selected. But of course, being in Canada, I can't get NASA money, so my funding comes from the Canadian Space Agency, which is a really great thing to allow me to participate. But then shortly after I was selected in 2019, I was asked to be part of the Project Science Group, which is essentially the leadership science council for the whole mission. And so this press release that was issued in February of 2020 has my name in there, which is really exciting, along with my colleague Tanya Bosak from MIT, who's an astrobiology expert. And this is really exciting for me in particular personally, because at the age of 13, this is me here at about that age, I decided I wanted to work on samples from Mars, and I wanted to be there when samples came back from Mars. So here we are. We've just collected the first 2 samples that will hopefully eventually come back from Mars someday. And I've been involved in this mission in that role. what's interesting is that, Gary mentioned it, but I did my PhD on meteorites from Mars, and we have over 160, I think it's like 165 now, different meteorites from Mars that have been blasted off the surface of Mars by impact and have made their way naturally to the Earth. And you say, well, why do we want samples from Mars if we already have the Martian meteorites? One of the things that my research and with others as well has demonstrated is that this process, this natural process by which Martian meteorites are lofted or launched off of Mars is quite a violent process, and it is biased towards younger igneous-only rocks, younger igneous rocks that have not been significantly altered. They have been weakened by alteration. The strongest are the ones that are going to make the trip. So the studies of the meteorites, even though we didn't have, we've got so many now, they show that over 80% of these 160 rocks are all 600 million years old or less. So remember at the beginning I was talking about how the really obvious life, the evident life that we have on the Earth kind of started around 600 million years ago. That's the oldest that one of these, most of these rocks from Mars are. There's a handful that are older, but most of them are really young. And so they come from places like Tharsis or Elysium, almost certainly, and are biased. There's a bias in the selection that nature makes towards the ones that are going to make the trip. And they're not sedimentary. This artist impression shows sedimentary with slime on them. They don't have those characteristics. And so what this mission allows us to do is to pick the rocks, the really old rocks, we hope, and pick the igneous rocks and the sedimentary rocks, and most importantly, the sedimentary rocks that might have evidence for life, and to choose those preferentially to bring back. So the plan for roving and sampling that we developed before we even landed looks something like this. This is an example where in this particular planning, the notional landing site was here, just off of the crater. And this is a geological map. This shows you the crater floor units in tan and green, and it shows you the delta units in blue, and other units in there's a marginal kind of units, rocks along the edge of the crater in this green, and then the crater rim itself in pink. And so we planned, and the general idea is to drive in this general direction. Although we've done this green zone campaign around the edge of Satan, we're going to drive back around it and all the way around this way and pick up this traverse in about a year's time. And then we're going to head up onto the delta to determine whether we do this excursion down here. We're going to head up onto the delta, collecting samples as we go, and then head on into this other area and then to the crater rim. And at that stage, we're going to take the samples that we have and we're going to put down half of them, approximately. So by that point, we'll probably have something like at least a dozen, maybe something like 16 to 20 tubes filled with samples. And so these tubes like this, each with a sample about that size, about 6 centimeters long and just over a centimeter across, of a wide variety of types. So we've already got 2 from the what's being called the mafic floor unit, and we'll probably get more from inside Seta. That'll be soon, probably in the next, after conjunction in the next in October, and others from whatever other great rocks that we encounter, and we'll put some of them down, and we're going to put them in a cache. So they'll be in the tubes individually, just set on the surface of Mars. So we'll put down this initial depot or cache of samples, but then we'll take duplicates of those and keep them on board and carry them with us and continue our exploration outside of Jezero Crater for the following 3 years and explore this incredible geological terrain outside of Jezero Crater in Neelyplanum for an additional 3 years, adding to our cache on board of samples, and then we'll make another cache, or we'll deliver those samples to a follow-on mission. So this is the scenario, at least based on current planning, for a 3-mission sample return campaign where we're here where sample collection takes place with Perseverance. And in 2028, give or take, there'll be a fetch rover that comes along and picks up we either hand off those samples or it picks up samples from one of our caches and puts them into this container, which has slots for the tubes sealed up, puts it on a rocket and blasts it off the surface of Mars. That container then ends up, that's the silver thing here, ends up being captured by an orbiting spacecraft, which then seals it up inside there, turns around and heads for Earth. With the earliest time that the capsule could come back based on current plans of 2031. So there'll be some time to wait till the samples are back on Earth and in labs so we can study. But basically what we're doing now and the significance of the mission and the excitement for me, my role in it, is that for the challenge is for us to do the job of collecting the best possible samples and a real diversity of samples that could hold within them the clues to whether life was ever actually on Mars. And we'll be able to then interrogate those samples in labs on the Earth in the next decade. I'll leave it there and take questions. Thanks very much.
Thanks, Chris. I don't know if they can see that, but everybody's clapping. Type of thing. Very interesting talk, type of thing. I assume there are questions. I've taken most of your time right now, so I'm going to let someone else ask the question first. Chris, any questions? Hello?
None so far.
None so far.
Oh my
got
goodness.
everybody stunned and still in thing. Well, let's do a general question so they don't scare. A lot of people say, why is Mars red? Is it because it's the main mineral or the main rock is peridotite? Or am I totally off my rocker?
It's not peridotite. I mean, there are minerals similar to what you find in peridotite, but the reason is two reasons. One is because the environment, as I mentioned at the beginning, the environment at the surface of Mars is such that it's dry, and there's something in the soil that oxidizes, that causes rusting. And so any iron that's there in the rocks will rust. So in that sense, it's similar to, sort of maybe the reddish color that you see in the tablelands, for example, in Newfoundland. But the rusting takes place, and that is coupled with it does have an atmosphere, just thinner, and lots of dust being produced in it. That dust is global, and you get these global dust storms that you may be familiar with, and where it obscures the surface, and that dust gets everywhere, and it coats everything. And so that dust is rusty, basically, and it's everywhere. And it's a function of its geologic history. Like we don't really, what I alluded to, this massive sort of change in the climate of Mars 3 to 4 billion years ago. It's a drying out, but it's also a loss of the atmosphere. It's a shutting down of the magnetic field. It's a whole series of things. It's cooling off. It's a whole series of things that took place to turn it into what it is today. And like I said, that's one of the big questions. So even beyond sort of understanding whether life was there, when liquid water was there, understanding that transition between the more habitable environments, more hospitable place to what it is today is what we're after as well. So those samples that I mentioned, they're going to be the ones that are from the lake bed or from the edge of the lake where we think there could be evidence of ancient life, but they're also going to be the ones that are representative of rocks of that time period, so that when we bring them back to the Earth, we can better understand what was going on in Mars geology and understand that transition.
Okay, we have 3 questions that have come in. And
All
the
right.
first thing that I personally thought of was, well, if all this rust is on the surface of Mars and there's all this oxygen locked up in the surface of Mars, there must have been a lot of oxygen in the atmosphere. But I'll get to the question right now. Bill Tucker asks, first of all, how is the core sample released from the bottom of the hole?
Good question. So what happens is that once it gets to the bottom of, or to the maximum drilling depth, then it stops and does Yeah, this is actually quite interesting. So what happens is, so the tube that's in there has an opening, and the opening to the that's slightly elliptical, and the opening then to the tube can be twisted. The tube relative to the bit can be twisted so that it breaks the bottom of the core off. It's an ingenious design, and if you go and look at some of those those images like I showed you of the core sitting in the bit, you zoom in on them, you can actually see a little bit of the edge of that tube because of that offset. So it's an ingenious way to make sure that that the core breaks off from the bottom of the hole.
Yeah, I'm doing renovations in a cabin bathroom, and I was using a hole saw in wood, and getting those little wooden plugs out of the saw is non-trivial. So, good question. The next question from Mike Morrow: is the oxidized mineral another potential source of oxygen for future missions?
I suppose it could be if you could unlock it. And getting back to sort of what your question is, Chris, that the oxygen didn't necessarily come from the atmosphere. It can come from the rocks. It's the chemical reactions that take place. You know, if you have an oxidant that can actually you basically turn your iron into rust, sort of reduced iron into oxidized iron, then you bind up more oxygen from other parts of the rock. So it's not necessarily kind of sucking it from the atmosphere. But in terms of liberating, I mean, there's people are looking at that sort of that technology to try to use it as a resource, I suppose. But the atmosphere itself is a big reservoir. It's easier to work with because it's already a gas. So that's the whole premise behind MOXIE, the instrument, to be able to take the existing carbon dioxide from the atmosphere and essentially split it and split off the oxygen from it.
Right. Marcellus asks, how much total weight in return samples when landing back on Earth?
Total weight in the samples themselves, the goal is a maximum would be something like 400 to 500 grams, depending on the density of the rocks that we get. So, and that was actually defined 10 years ago. I was on a what's called a science assessment group, or a SAG, to look at Mars sample return and what you need kind of end to end. And it was decided, we sort of came up with that general number of like 400 to 500 grams of material of a certain number of samples. And when you kind of do the math, then it works out to between 30 and 40 samples, sort of 10 to 15 grams each.
And a lot of dollars per gram.
Mm-hmm. A lot of dollars per gram, that's right.
Mike asks again, earlier in your talk, there was an image with ingenuity in the distance and perseverance in the foreground. Was that an artist impression? And if not, what took the image?
That was a selfie, and that's taken with Watson. So that imager on the end of the arm can look back. It can focus to infinity, and it can look back at the rover and take a series of a series of images that get stitched together into a selfie. And so there's some image processing there to kind of process out the arm where you get the overlap, but basically that's how that's taken. And stay tuned, because there should be a selfie being released. I saw it in the team. There should be a selfie being released of the rover sitting after taking its first two samples at Rochette in the Citadel area. So there should be a Citadel selfie coming, being released publicly soon. It's going to go on my background.
You must be happy.
Yes.
I noticed, Chris, I've got a quick question here. I've got one of the images that you had of where you had the samples that were planned. not in a very specific sense, but there was a slide that you had there that had the ones that were going to be cached versus the ones that were going to be kept with the rover to carry on. And at the end on the right-hand side of that was a blank. What's the thinking behind caching and keeping a blank? What's the blank for?
That's a good question. So the blank, this is a really important thing that people and maybe sort of underappreciated, but if you work in labs, a blank is something that goes through everything that your sample goes through, but without a sample. And so allows you to track potential contamination. So when you're collecting samples like as important as these, let's say they call them marginal carbonates, the ones along the rim of the crater in green here. They have a signature of carbonate minerals, like limestone sort of thing, from orbit. Whether that's actually, in the form of limestone is, it's not likely limestone, but what form that's actually in and whether it was, say, precipitated in the edge of the lake kind of thing, and whether life was involved, that's all up in the air. But let's say that we roved up to that and found a stromatolite, right? Or something that looked like a stromatolite or possible stromatolite. We're definitely going to take a sample of that. But in the labs on the Earth, we want to be able to interrogate that, including not only what you see in the rock in terms of the structure, but also any organic molecules, because that could be organic molecules from life that existed 4 billion years ago. But if you have organic matter that's contamination from the rover itself, it could obscure that. So the whole idea of blanks is to be able to take a snapshot of what might be coming off of the rover at different parts in its history as it roves along, as the the mechanics sort of continue as machines do, they wear out or they degrade or what have you. And so different stages will take blanks. Now there are specific tubes designed for this. There are tubes that are designed not to have samples in them, the same size as these, but instead of being able to take a core sample, they have a bunch of materials of different types, different surfaces, things like sapphire or other sort of aluminum and things like that are meant to sort of grab anything that might be floating around. So at certain stages in the mission, we'll take out one of these and kind of wave it around, I guess you could say, basically put it in the inside of the end of in the coring device, not actually put a sample in it, and then store it away. So to provide a snapshot of what was coming off the rover at that particular time. There was one actually loaded inside of the coring device during launch and landing. So that's called the bit carousel, I should say. So it's sort of in the rover. It was sitting there exposed to the rover, basically not in the arm, but in the rover itself. That's right. It's called the bit carousel witness tube, and so that's already been processed. But it was sitting there open to be able to record everything that was happening, essentially up to landing. So yeah, we're going to have those, and then we'll split them up between what gets cached in the first cache and what gets carried along with us. But it's an important component of understanding if we have any organic molecules, especially once we get things back on Earth.
Cool.
Sort of a science 101, the ever-present baseline.
Anyway. Exactly. Yeah.
Mark Pippi asks, how deep was the water in the crater, and how long do you think it lasted in the crater?
Oh, that's a great question. I should have actually mentioned that by some estimates, the water was at least 100 meters, maybe 200 meters deep, based on the inlet and the outlet that I showed you, the elevation relative to the depth of the crater. So pretty deep, and thousands of years, maybe tens of thousands of years. The estimates are not clear, but that's one of the other reasons why we want to take a close look at the delta, because when you look at the cross-cutting relationships, or even especially if we're able to get more than one sample of different phases of the delta, different types, like you have here noted delta thinly layered, delta curvilinear. In other places, there's delta blocky. So sort of these are just sort of descriptors for what we see from orbit, but they probably correspond to different time frames that the delta was active, or potentially different time frames. So if you were to get those samples and then determine when those rocks were laid down, you could get an idea of the minimum amount of time that river system was operating. So it's an open question, but the estimates I gave you, like up to 200 meters depth and maybe thousands of years, maybe longer.
Wow. Jamie Kenny asks, do we expect to discover if the water was saline or fresh or something else entirely?
Yes, that's a good question too, because if you look at the most recent results, there was a press release last Friday, actually, a press conference from NASA talking about the successful sampling, and some of the imagery that we got of the abraded patches that we did on these rocks show salts. So that actually there's igneous minerals, but there's salts as well, and that's really intriguing because, of course, those salts are almost certainly from liquid water, and particular minerals that are there, if we can identify them with the rover instruments, but also if and when we get them back on Earth, we can say something about the chemistry. And so, yes, we should be able to determine fairly well whether that water was saline and also what its pH was, etc.
Very cool. No new questions for a few seconds.
Then I'll wave and say hi to Robbie. I see her there. Robbie and I go way back. She was
Hey,
my
Robbie.
TA at Queens.
Oh, wow. Okay.
The other rovers have picked up methane seasonally. Has this rover picked up any methane?
We're not equipped to look for.
Or
No, we're not equipped to look for methane. So that's the Curiosity rover has been able to analyze methane in the atmosphere, and we haven't been able to do that. So yeah, we're blind to that, but maybe the samples will tell us something about the environment in which methane could be produced, for example. We'll see.
Mm-hmm.
John Pippi asks, who gets to analyze the samples when they return?
Well, hopefully me, but among others. That's a great question, and in fact, there's a whole set of committees, I guess you could say, working groups that have to do work between now and 2031 and they've already started that process. So there's a Mars sample return working group, and then a second iteration of that I haven't been involved in, but others have. Kim Tate from the Royal Ontario Museum is on those, and their job is to do things like define what the science is, how the samples get treated when they come back, and also right now to define the facility that's required to curate these samples, because this is the first time we've done this. We will have done this, is bring samples back. There is a small but non-zero possibility that there's extant life, not just extinct life, but extant life in the samples, and we want to make sure that they're safe. And so there's all these and all this preliminary, what they call preliminary examination, this detail and cataloging of the samples that needs to be done in a dedicated facility prior to them being released to people all over the world. But the idea is to release subsamples to people all over the world, to researchers like myself who can, or Phil or Robbie, or people who can write in proposals to say we want to do this or that specific thing on this particular sample for this reason. And then those subsamples would get allocated to people. That's the way that NASA has done it with Apollo samples for over 50 years, and meteorites and the way meteorite collections do it as well. So that's the whole idea.
So in the related vein, what kind of discussions and decision making goes into finally deciding to sample here and in the rover activities, and then what are the plans? Because it's always you got to plan out. Okay, well, we only have so many tubes, right? So you can't sample everything. So you
Yeah.
always have to make very careful selections in doing the field work and figuring it out. So what in a snapshot, what kind of goes into that kind of decision making?
Well, Phil, you probably hit on one of the most challenging things for this mission, because this whole plan that I have on the screen here, this plan is one possible plan that was worked out. Give it, under the assumption that we landed in this site right here, just off the Delta. And the exercise within the team was to go, okay, you have one Mars year, okay, so 2 Earth years, and you want to collect 18 samples by the end of those, including duplicates by the end of that time. Where do you go? And you're given this many number of sols or Martian days to do sampling, and this many to do traversing, to do the driving. And it's a challenge. It ended up being a challenge. So that those plans exist. The current plan though is more than a Mars year. It's a year and a half, which is 3 Earth years, to get us from where we are now in the green zone to this crater rim depot, by breaking things up into about 1 year periods. So the green zone campaign that we're in now, and driving around Sept to this area right here, that's 1 year after landing. So actually not that much time. February next year, we'd be up and around here like this. Then we'd spend another year driving up onto the Delta, and then another year kind of in the marginal part and up into the crater rim. So that's kind of how it's broken down. But there's a budget. There's a time budget and a sampling budget, and they go together. And right now we've budgeted like 11 Martian days, sols, to do everything we need to do to take a particular sample. And so, and a few days after that, not the same number duplicated, not another 11 days, but a few days to take a second sample in a pair like we just did. So that's all gets factored in. And then, of course, coupled with that is, okay, what specific rocks do we want to get samples of? What are the priorities? So we've already prioritized that. We already know in the budget of the sampling and timing budget of the green zone campaign, in order to kind of do everything we want to do and get the samples we want to do in a year, we want to take 2 unique samples from the crater floor fractured rough. So we have the ones from here from Citadel, and we'll probably take another one from as we go back. But then we're in Sept here, we're in a different rock unit. We know that already. That's all I can say. But yeah, we're going to take at least 2 samples, at least 2 unique samples from there, because those are crater floor units that are important to understand. And then we'll drive out and out and around. And we have the budget for an additional 1 or 2 samples if we come across something else that's interesting. But then we have to get to kind of this point right here by, kind of early part of next year, by like kind of February, March of next year. So you have to budget that. Yeah.
Yeah, that's really neat. It's there's a lot of very careful weighing of options to do in all of that, but it's going to be driven a lot by what you find. So it's a nice problem to have.
It is a nice problem to have. Absolutely, yeah. It's a really interesting problem to have, and it's really interesting because the approach is so different from Curiosity or any other mission that's gone before, which is to say that which the sampling aspect is the difference, and whereas Curiosity has gone slowly but surely up this mound of sediments in Gale Crater, doing as much as it can all the way along, essentially applying its instruments as best as possible. We actually don't have the luxury to do that. We can't just throw everything that we have on board the rover at all the rocks, because we have to sample as well. So there's a kind of a give and take, or you have to factor in, like I was describing, you have to factor in the sampling. and that has not been done before. So they may come down to, you know what, we have characterized this particular rock. We might come across rocks in the next few days as we're in this South Sept area, and we go, wow, this is really interesting, really complicated, but you know what? We don't have time to sort out all the relationships because we just don't have the time to spend, you know, with like abrading everywhere and putting the arm down, the instruments on the arm down and getting all this information. We don't have the luxury of that time so we're going to take a sample with its documentation, which is really what sets the samples apart from the meteorites, where we don't know exactly where they're from, is we have the documentation of exactly where that sample's from and everything about it, and the abraded patch nearby, which we think is tells us what's in the tube. And then we've got to move on and trust that we have enough information so that when it comes back to Earth, that's when we can really tease out the full story.
Wow. Must be frustrating, or frustrations are going to come, I expect.
But yeah, potentially. But I think if we have that approach and that understanding, and I think the team has that understanding, going into it, that you know, this is the overall approach. We're going to do some really great science. We're going to publish papers on the geology of Jezero crater, no problem. But that there's more to come in the samples. That there are additional questions that we have to wait to get the answers for, and that's the ultimate one of the main goals of this.
Speaking of additional questions, Mike Morrow asks again, are there any other rovers planned between now and 2031?
No, there aren't any that I'm aware of other than the Fetch rover to get the samples. They're not by NASA. The European Space Agency has the ExoMars rover, which has been delayed a couple times, but it's supposed to launch next year. And it's not a sample return mission. It has a drill though to drill into the subsurface, and it has instruments on board to be able to look for evidence of ancient life. So that'll be interesting to see how it works.
Oh, no more questions. And I know. What?
I was just going to say, how on earth did Perseverance rate Mars like that?
Yeah. Yeah, that's right. Yeah, it's one thing to kind of have tracks that start from nowhere because you landed, but yeah, this was extra tricky. I guess we needed the helicopter's help for that.
Yeah.
That's what. Yeah.
All right, I'll stop sharing now.
Okay. Well, I know Chris is in another time zone, and it's his time zone to go put on the feed bag, get something to eat. So I'm going to, if he wants to sum up, and then he can go. And I want to thank him very much for this excellent talk, this eye-opening talk. I mean, I thoroughly enjoy it. I've got so many questions. I'm going to keep to myself because I'm getting dumber and dumber as I get older and older. But Chris, you want to do a sum up before you go? And I want to thank you. And I think we have your address because I think Randy has a little gift to send you from the center. Do you, Randy?
Yes, I do.
Shake your head, Randy.
Well, thanks very much. That's very kind of you. And really, it's a pleasure to talk to you, to share my excitement about this with you, and hope to see you someday in person.
Yeah. Next,
You're here.
A meeting out at RASC. I'll see if I can go out and see you again. Been a long time.
Thank you, Chris.
Absolutely.
Talk about good time.
Yeah, that's right. Okay, I'll sign off. Thanks very much for having me.
Thank you.
Thanks, Chris.
Thank you very much for having us.
Thanks a lot, Chris.
Excellent.
See you soon.
Okay.
Anyway, Jim sent some pictures, some beautiful pictures here. M57, the Bubble and Lobster Nebula. In the constellation Cassiopeia. Nova V1405, Cassia March 18, 2021, binary star system, white dwarf, sunlight star, orbital period of a few hours, exclamation point, solarated disk, and fusing hydrogen, increasing velocity. He used a LE enhanced tri band 180 minutes plus red, green, and blue stars 30 minutes, 3 hours total exposure. This is with his Canon 500 f4.5 lens. Wow. And his Sony modified A7 camera, 180-second exposures, unguided, on his Optitron 40 mount, processed in Pixel Insight and Lighthouse. Oh, I'm sorry.
Lightroom.
He was saying that Jim has an article in this month's Sky News, not an article, a picture actually published in this month's Sky News. In the news, also in the newsletter, our local newsletter, but he's also got a picture in Sky News this month that he processed for the RASC camera. Now, I don't know, I was hoping he'd be there to talk, but
Yeah,
I'll go on to
sorry.
the second one.
Okay.
I think I crucified the
you
first
did-
one.
You did a good job on the first one there, Gary.
Okay.
Yeah, sorry, no one, I was muted by the somebody in charge here, so.
Yeah, I am tried to unmute you, and I guess when you said to unmute, you muted yourself again.
Oh, I don't know. I couldn't get on. Anyway, no worries. This is actually a very short exposure. I remember we were out with Robert at Butterpot Park for this particular one, and this is just after sunset, and I was able to get only about 30 minutes of exposure time before it clouded over, and so like the article I did for the newsletter, it was guerrilla astronomy at its best, because you take what imaging time you have and you do the best you can with it. And I actually think that this turned out not too badly. This is the Lagoon Nebula in the direction of Sagittarius, which is the center of our galaxy. And in this particular wide field shot, you can see that there's a whole lot of dust and obscuring dust that basically hides the center of our galaxy from being seen, except for some small areas like this Lagoon Nebula that basically, and the Trifid Nebula, which is up at the top right there. And this is with the Optolong tri-band filter. So it's basically H alpha, H beta, and oxygen 3 being imaged here. But you can get a sense of that there's in between the gaps and the dust, you can see the tremendous density of stars, and this is quite an impressive sort of thing. So there's a number of different things here. There's the Messier objects, the Lagoon Nebula there, and the Trifid Nebula, but there's also some small nebulosity in the small clusters. Like if you just stop right there, or go down towards the lower, that right there is NGC 6544, and just to in the Lagoon Nebula itself is you have an open cluster, NGC 6530, and then up to, as you go towards the upper left, you see features. These are little features, nebulosity there. That's 6559 that you were just pointing at there, Gary. So good job. And so that's a rather pleasing image of that Lagoon Nebula, which I was quite fortunate to get in a small window of opportunity.
Actually, it's a
During the
beautiful
summer.
image, one of the best ones I've seen in a long time of the lagoon area.
Gorgeous
Beautiful.
picture.
Now, do you have another one here?
Yeah, and this last one was, I guess, the third time we had some clear night, and then Yolanta and I were in Terra Nova, and this was I guess the challenge that Randy was posing for us is we spent several days around the full moon, just prior to the full moon, trying to find interesting angles and shots in town. But on the Sunday of the full moon, we ended up going out to Terra Nova, and we set up that night. I guess it was the only night in our holiday for that two-week period that actually was clear. So we had an opportunity to grab a shot of the full moon rising. So this is with the 300mm lens and my Sony camera processed in Lightroom. This was taken from the visitor center in Newman Sound. So
Beautiful picture. Beautiful. Love the detail. You can make the young woman out. See, there's her nose, there's her mouth, there's her nose, there's her eyes. That's her hair right here. Everybody see my woman? That's her ear.
no, I can't see.
Okay, here's the chin.
No, it's not.
Here's her mouth,
Anything. Okay.
her nose,
Oh, yeah.
her eyes, and this is her hair. And she has a pearl necklace down here with a great big pearl in it, which is
Need some drugs
Thai
with it.
crater, but that's hidden by the trees.
If,
That's
A
my
bit like
interpretation.
Wilma Flintstone. Looks a bit like Wilma Flintstone looking left.
Okay. Yeah, actually it does. I'll agree with you there. Or some people also see the pioneer woman. This is her head with her bonnet. This is her prayer book, the Bible. This is her belly, and this is her dress. Now,
in
I'll go
Taiwan,
get another drink while you're looking at that.
in Taiwan, they see the, instead of the man and the woman or the woman in the moon, they see a rabbit.
Yeah, well, there's the ears of the rabbit. Yeah, I heard Play by Bunny also. Paid lots of money to get that rabbit up there.
Anyway, that's it for me.
Okay, Mike.
Okay,
Okay, yeah, there you go.
yep, so, yeah, so this one was, just from a few days ago. It's M27, I think it was, about, half an hour using, from my backyard. I was trying a few different things, but, this is the one that I could see. Not much red because it's an unmodified DSLR on an ED80, and processed with Deep Sky Stacker, and then adjusted a bit with GIMP. So not much more to say about that. A couple nights ago.
Okay. All right. People got to start sending the pictures in. It's pretty hard to find them over the emails and stuff like that, by the way. Nice job, Derek. Lovely.
Thank you.
Yeah. Sometimes called the Sun-Stun Nebula. So dumbbell. Okay.
Yeah.
Now we're moving on to Randy. Thanks.
Now, yes, okay. So on the left there, you can see that's Sky Safari, and I was doing Nikolai's challenge. So that was Sunday night, was it? So just to show you, easy to spot where Jupiter and Saturn are, and that Capricorn, and you know, make note of that. Fomalhaut is down there, and that cloudy type thing. If you look at the two little stars there, I use that as a pointer down to it. So I think I proved that that was actually Fomalhaut. And if you go to the next one, I took that picture and submitted it to astrometry, and they did a partial job on some of it. As you can see, Jupiter and Saturn weren't labeled, but this is Austrinus, and I'm pretty sure that's Fomalhaut. And since Nikolai's not here, I'll have to wait till December meeting to get his approval of finishing the challenge.
Very good. Excellent. Now, that's it from Randy. Thanks very much, Randy.
Are you stealing these from the newsletter?
No, these are emails that people sent me. This is Bernard's not here right now. I guess he's probably out in the field. Bernard has an observatory on top of a hill out in just out past Lewisport, and the winds are usually around 100, and he has cables holding his observatory down, plus his cabin. So I don't know if it's still there. Of course, he didn't get the hurricane, so pretty good. But this is one of these pictures of Saturn that he sent, and I just couldn't get over the detail. Look, you can actually see the hexagon here on the bottom. Unbelievable. And the details in the bands, the shadow from the ring, Cassini's gap, some of the detail. Excellent picture. I have to say, that's one of the better ones I've seen in a while. What'd you say, Randy?
That's in the newsletter.
Okay. And everybody can get the newsletter by going to the website?
Yep. So click on Center Newsletter, new.
Yeah. I think it's 10 pages, is it, or 20 pages?
20 pages.
20 pages of local news and images. Wow. I don't know how this works. Phil, you got anything to add, Vice President?
No, not right now. Thanks, Gary. The only thing, I think there was some recent discussion of just about the long-range planning at this point for the 2023 solar eclipse, 2024 solar eclipse, sorry, coming up in a few years' time. And just some long-range thinking on what we would like to do as a center for that. You know, maybe some point at one of our upcoming center meetings, it'd be nice to have a kind of more focused discussion on that and figure out, you know, what kinds of things do we want to do, you know, aside from just going out and looking at it, which we all do. But, you know, in terms of public engagement, the eclipse path goes right through the heart of the island. And, you know, if we get good weather, fantastic. If we don't get good weather, it's still an interesting and useful event. So, you know, I think it'd be worthwhile and a good thing for the center to do, to figure out what we want to do about that, what kind of effort we want to put into it, in terms of public outreach and so on. Yeah, I think there's a lot to talk about with that at some point, but, you know, we've got a bit of time. Hopefully we'll be totally
99%.
Yeah, and go right through central. Most of the island actually gets totality of some kind or another.
Bass,
yeah,
Terra Nova.
So I think it'll be, Newfoundland might end up being a decent tourist destination. I mean, it's April, but you know, it might end up being a decent tourist destination for some people. For that,
it's 70% cloud,
right?
Average in that area.
Yeah.
Now, Nikolai was telling us that if it's usually at that time of the year, if it's cloudy on the East Coast, the West Coast is clear, and vice versa.
Yeah.
So he said, you know, if you got 6 hours to make up your mind to head west, if the East is covered up.
Yeah, so you wake up in the morning in Grand Falls or something, and then decide which way you're going to break. You know, it's like the you know, the goalie covering the net. You know, which way you're going to jump. But you know, that the eclipse itself happens in the late afternoon local time, so there is all day to do something about it. Yeah.
Randy, you've been attending a few meetings on that, haven't you? Over the months. Yeah. Okay, so anybody who wants to talk can tune in. You should be able to just unmute yourself.
Owner, by the way, is Sue Hart.
Now that I can, I don't have anything else to say.
Well, further to what Phil was saying, if everybody goes to Bonavista, that's going to be an issue for trying to do any public outreach in town, right? If everybody leaves town.
Yeah.
I did some observing during that storm, by the way. It cleared off about 4 o'clock in the morning. It was still windy, but I could see the sky.
I during the storm, wow, that's I was out on the Saturday evening after, because the observatory offers some wind, but I think people have been reading on the list. I took all these great exposures, I thought 5-minute exposures, and then saved them all as a garbage compressed format, and Bob's your uncle. Got nothing out of it, really. Nice exercise.
Nice moon. The moon is out again tonight, or it was.
Oh, yeah.
In the cloud now, but
Hmm.
I was out last night looking at it, and the night before.
That was my next question. If it's actually going to be clear tonight, I'm not so sure. But
It's cool. It's only 9 degrees out there now. Frost in a lot of places overnight. Yeah, that season is coming.
Yeah.
Remember,
Chris, have you been using your 2x54s?
not since Grossmorn, actually.
Okay.
Not since we've been back from. Oh yes, so when the other Chris Hurd said peridotite, and someone else said peridotite. Yeah, surrounded by lots of peridotite for a little while. But no, not since then. I do like them. I had them at the cabin once. How do you
Yeah,
like
no,
yours?
Yeah, no, I like them very much. I haven't been to a proper dark sky, but they're really, they work better with better seeing conditions. Like I've picked up things that I never thought I would have, like the dumbbell nebula.
Yeah.
The one I'm having trouble with the most is the coat hanger. I can always see the hook, but I can hardly ever see the straight line.
Oh wow.
I've almost got to use averted vision to find a straight line, unless it's an
Wow.
exceptionally clear night.
Wow.
Yeah, the
But, you know,
Brock eyes, or whatever the official name is, the coat hanger. Yeah, it's one of those annoying things that pops out so easily in any photograph you take.
Yeah.
Even a quick DSLR snap, right? But seeing it visually is yeah, you're right. I don't think I've seen it visually.
how much can you get in yours? I can actually fit the entire Big Dipper, not Ursa Major, but the Big Dipper, you know,
Yeah.
balls at the end of the handle. I can just
Yeah.
fit that in my field of view.
Yeah, it's the
So-
same
So
field.
it's about 25 degrees.
Yeah, they claim 36. I'm happy saying it's about 24, 25, somewhere in that ballpark with my eyes and my face.
So have you tried to find the North American Nebula with them?
Again, I've only used them down here in the Cove. So I really want to get out to a dark sky. Like on good seeing nights, I'm really impressed with how what I can see. Like I said, I didn't think I'd ever see like something like the Dumbbell Nebula down a little old Sagitta while I was looking for the Brochies cluster, right? And the globular clusters. And I haven't, I thought I'd seen a smudges for 81 and 82, but I can't claim that I've actually seen him yet. It's where it should be, but it wasn't defined enough. Have you
Yeah,
shot him in 81, 82?
I'll be honest. I was a bit distracted. We had clear nights for a couple of nights at Grossmorn, and I didn't break them out. I was helping people with campfires and things, and then I was too darn tired. But I should make some dedicated trips out to Witless Bay Line or something with these, and a zero gravity chair, and spend some time under a dark sky.
Yes, lying down, they seem to be best. Your maximum exposure lying down.
Yeah, absolutely. An opera glass handle or something to hold them up wouldn't be a bad idea either.
Yeah, I've come across these things, bino blinders, like the neoprene cups that fit over the end, just to tighten up to your face, which are kind of expensive. I'm working on now getting a couple of those, those beer can cozies you can get.
Oh yeah.
A couple of them in black and cut out holes to put him in. I think that'd work for me. I'll show you when I get one made.
These,
Or
you
just
can
wear
get
a
these
parka with a
safety
hood.
you can get these safety goggles, right? Just tear the lenses out of them.
There you go.
I've looked at some of that stuff in the Princess Auto Net, and I haven't seen anything that I could convert. But I know that if I had a couple of those beer cozies, because they already got little holes in the bottom,
How
just
about a
make it
scuba
big enough.
mask? How about a scuba mask?
I do have one of them, yes.
Yeah. So, you don't even have to take the pipe off. You could you could breathe through it, right?
Yeah. Or a really tight fitting like a hat thing. But I think just a little, the neoprene cups, just the stray light really gets to you.
Mhm.
Hey, we're going past 9:30. I thought we'd be kicked off by
Yeah.
Roland.
Yeah, well, we took that.
No
For
problem.
those people interested in the moon, this is a great book.
Bob King wants to come in.
398 features. These are features that people normally don't look for. Excellent book. I'm working my way through it. He has another one out that I want.
Where'd you get it?
On Amazon, actually. And make sure you get the second edition.
Features
Yes.
of by who?
By John Moore.
John. Oh, okay.
The second edition, he's added not only the maps to show you where everything is, but the geology of the area.
That's cool.
Really cool. It's
Wow.
so get the second edition, not the first edition. And he's also got another one with other features, which I've ordered. I was just so impressed with this book. Being a moon guy, I really like it. It's nice to, to go after things that not everybody else goes after anymore.
Most people are after
more like
the X and
It has-
the Y and the V, right?
Yeah.
Yeah, it has
Although-
your view to your scope, and that close up. All amateur taking pictures too.
Cool.
Is tonight you can see the wall?
Yeah, it's
I thought I saw something. I thought I saw
around.
something about
If it's
that.
around first quarter or stuff like that, you can see the wall, the straight wall.
So that's features on the near side of the moon.
Yeah, he also has features on the far side of the moon, but I don't know why.
Yeah, they're
I
hard
was
to
going to
see.
say volume 2.
You need to put an extra
But he
mirror
also
up
has,
your telescope, right?
He also
You have to
has
have a
one
mirror
just
out
on
behind the moon.
craters.
The RASC calendar says the wall was last night.
Yeah.
Shoot. Oh, well.
A good thing to do with the wall is actually do a measurement to see how measuring the shadow and the thing and figuring out how high it is. That
Right.
is cool. I did that a couple of times. Type of thing. Anyway,
I need to make friends with the moon. I generally just think of the moon as something that blocks out everything
Like
else.
yeah. Well,
Well, next weekend is another moon challenge time.
Yeah.
anyway, I guess we should sign off. Anybody got
Yeah.
anything
Yep.
else? All right. Good night. God bless
night.
everybody.
Yeah.
Good night, all.
Take care, everyone.
I'm getting religious.
So long.
Sorry about that, Gary.